A basketball team ends the game on 87 points. Ask how many ways 1, 2, and 3-point baskets could have added up to that, and you have our second numeric recursion. Where Fibonacci branched 2 ways, this one branches 3 ways, with 3 base cases to match. It also hides a subtlety worth catching. In basketball, a basket is worth 1 point, 2 points, or 3 points. So the question is, how many combinations of 1s, 2s, and 3s add up to a given score? And the lecture says, order does not matter. Hold on to that phrase. We will come back to it. It is hard to say when you would need Fibonacci in real life. This count is a bit more useful. We could certainly do it iteratively, brute forcing our way through every combination, but we are going to think about it recursively, and the recursive view turns out to be beautifully simple. Recursion needs base cases, and here there are 3. For a score of 1, the only way to get there is a single 1-point basket, one way. For a score of 2, you could score a 1-pointer and then another, or a 2-pointer outright, 2 ways. For a score of 3, you could score 3 straight 1-pointers, or a 2-pointer and a 1-pointer, or a 3-pointer outright, 3 ways. So a score of 1 has 1 way, a score of 2 has 2, and a score of 3 has 3. These 3 counts are hard-coded into the function, and they are about to guide everything the recursive step does. Now the recursive step. Take a realistic team score, say 87. We are past all 3 base cases, so think recursively. Every route to 87 ends with some basket, and there are only 3 kinds. If the last basket was a 1-pointer, everything before it made 86. If it was a 2-pointer, everything before it made 85. If it was a 3-pointer, 84. Picture replaying the game backwards, rub out the final basket, and what is left is a shorter game scoring 86, 85, or 84. Every route lands in exactly one of those 3 groups, and none is counted twice. So the count for 87 is the count for 86, plus 85 plus 84. The base cases feed the recursive step, 3 ways to score, 3 branches. Here is the whole function. The docstring says it returns all the ways to make a score of x by adding 1s, 2s, and 3s together, where order does not matter. Then come the 3 base cases, 1 branch each. If x is equal to 1, return 1. Else if x is equal to 2, return 2. Else if x is equal to 3, return 3. Exactly the counts we enumerated by hand. Otherwise, the recursive step. Make a score of x minus 1, then finish with a 1-pointer. Make a score of x minus 2, then finish with a 2-pointer. Make a score of x minus 3, then finish with a 3-pointer. So the function returns score count of x minus 1, plus score count of x minus 2, plus score count of x minus 3. Add those 3 counts together, and that is what the function returns for x. Run it and the counts climb quickly. Score count of 4 is score count of 3, plus score count of 2, plus score count of 1. 3 plus 2 plus 1, which is 6. Score count of 5 is 6 plus 3 plus 2, 11. Score count of 6 is 11 plus 6 plus 3, 20. Keep the chain going up to a score of 13, and the answer is 1431. That is the payoff of thinking recursively. 3 base cases and a single recursive line. Written iteratively, this will be a mess, a pile of nested loops, brute forcing every combination, and not remotely Pythonic. Now the subtlety I promised. Count the ways to make 4 by hand, 1 and 1 and 1 and 1, 2 and 1 and 1, 2 and 2, 3 and 1, and you get 4, not 6. The recursive step counts the order the baskets went in. The base cases do not. Working out that mismatch is the sharpest thing you can take from this example. The trace works like the Fibonacci trace, except 3 paths must be explored before each call can return. A score of 6 first explores a score of 5. 5 is a function call, so it must be resolved before 6 can touch its other branches. 5 explores 4. 4 hits pure base cases, 3, 2, and 1 return immediately, so 4 returns a count of 6. Back in the 5 call, 3 and 2 are base cases too, so 5 returns 6 plus 3 plus 2, 11. Back at the top, the second branch works through a score of 4 all over again, another count of 6, and the third branch, a score of 3, returns 3. 11 plus 6 plus 3 is 20, after 13 function calls. And notice the waste. We recalculated the score of 4, having already calculated it deep in the left branch. That repeated work is the same disease as naive Fibonacci. Score count is just as inefficient, recomputing subproblems it has already solved. The cure is the same too, memoization. Keep a memo, a dictionary, and store each score's count the first time you compute it, then look it up ever after instead of recomputing. The Python file for this lecture leaves that as a take-home exercise. Add a dictionary to score count, exactly as we did for Fibonacci. The pattern travels well beyond basketball. 3 ways to score means 3 base cases and a 3-branch recursive step. The base cases feed the recursion, the code stays short and clean, and the memo makes it fast. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.